Hello friends, in this lecture we'll be starting about how to find out the stability of a system and what does stability of a system mean. Okay, so suppose we have a transfer function that is equal to 1 by s plus 1. Okay, so and we again have a transfer function which is equal to 1 by s minus 1. So what does it mean by whether the system is stable or not? We need to find out. If we do a Laplace inverse of this, what do we get? We get it is e to the power minus t, right? Tut. And if we do a Laplace transform of this, we get e to the power tut. Let's draw it in the time domain. E to the power minus tut brings us something like this, right? And if we plot this graph, what do we get? We get a graph like this, right? So you only tell me, is this system stable or this system stable? This system goes to an infinite value when time tends to infinity, and this system tends to a finite value or a zero value when the time tends to infinity. So this is a stable system, but this is not a stable system. This is the criteria that we take into account when we talk about the stability of a system, whether the output of the system is reaching a finite value at time t equal to infinity or whether it is reaching infinity. Okay, this is how we calculate whether the system is stable or not. Now it is not possible if we get suppose a fourth order or a fifth order transfer function and we find out the graph from that equation. So we need to find out some way how we can predict that whether the transfer function is stable or not by just looking at it. Okay. So we have one idea till now, that is we know what this is called. This is a pole. This is s plus 1 is the pole. So if s plus 1 is the pole, now what is the value of s? We get s equal to minus 1. And here s minus 1 is the pole, so s is equal to 1 is the pole out here. So we can see that if the pole is on the right half of the s plane, this is the real axis, this is the imaginary axis, right? That if the pole is in the right half of the s plane, then the system is unstable. Now remember, this is only for causal systems. If the system is anti-causal, then the whole thing becomes opposite, and if the system is non-causal, then everywhere it's stable, right? Or it's depending on the ROC of the system. And in the left half of the S-plane, it's stable. So we can say that the imaginary axis is the margin from where we can say if it is stable or unstable. Now suppose if anything lies on the imaginary axis, if a pole lies on the imaginary axis, whether it will be stable or not, such a situation it is called as marginally stable. If any pole lies on the imaginary axis, obviously two poles will lie because it will be complex conjugate poles. Such a system is known as a marginally stable system. Okay. Now let us go into details with this. Now, first of all, we need to know what a characteristics equation is. Suppose we have a transfer function GSHS is equal to s plus 2 by s square into s plus 3 in s square into s plus 3. Suppose this is the s into s plus 3. Say this is the transfer function we have. Now, if you know what the closed loop transfer function would be, it will be this GSHS by 1 plus GSHS, right? So if it's always a closed loop system, so we have a unity feedback. Okay, unity feedback, so that will be GSHS by 1 plus GSHS. So the denominator part is the part that we need to stress on, because if that part is equal to 0, then the system is unstable. So we need to equate that to 0 and find out the stability and instability criteria from there. Okay, so first we need to find out 1 plus GSHS, and equating that to 0, this is what we call the characteristic equation of a system, right? This is what is the characteristic equation of the system. Now, the first, it was Harvard's criteria. Harvard's criteria was saying that if we have the characteristic equation, say s square plus 2s plus 4 equal to 0, we can predict that whether the system is stable or unstable directly by looking at it. That is, we can say that this system will be stable because it has all the powers of S. That is, the first criteria of his were that the system should have all powers of S and with the same sign. That is, if we get s square minus 2s plus 4 equal to 0, that's not a stable system. This is a stable system. Also, if s square plus 4 equal to 0, this is also not a stable system because it does not have all the powers of S. So this was widely accepted that this Routh's criteria would be the ultimate criteria that determines the stability of a system, that whether the system is stable or whether the system is unstable. But then there happened some problems because the criteria was always not satisfied. There are some systems where we can see that there are all powers of S, but even that the system is not stable. Let us show you an example of such a system. Say a system is s cubed plus s square plus 2s plus 8 equals 0. Okay. So it has all the powers of S. So Routh's first criteria is satisfied. All are of positive sign. So the second criteria is also satisfied. Now let us apply my let us apply the vanishing method and find out whether this equation is stable or not. Okay, applying my criteria of vanishing method, we can say that s equal to minus 2. If we put s equal to minus 2, that becomes 0. So this equation can be reduced to s plus 2 into, taking into common, it will become s square minus s plus 4 equals 0. Right? So s square minus s plus 4 equals 0. That will give me two values of s if we solve with Acharya. Let us solve the two values of s and find out. So this is s cube minus s square plus 2s square, right? So this gives me s is equal to minus b, that is 1 plus minus root over of b square, that is minus 1 square 1 minus 2ac, sorry, minus 4ac, that is 4 into 4 16 by 2a, that is by 2 into this, a is 1. So we get that half plus minus root minus 15, so that gives half plus minus root 15j. That's what we arrive at. So the pole would be located somewhere at half and plus minus root 15j. So this is definitely not a stable system, first of all because these poles are lying on the right arm of the S-plane, that too complex poles. So it's not a stable system. So these type of equations led to the point that Routh's criteria alone is not capable of deciding whether a system is stable or not. That's why we needed another criteria, which is the Routh-Hurwitz criteria. That is, we need to find out the Routh-Hurwitz matrix and thus need to see how the Routh-Hurwitz criteria is satisfied. We will discuss about the Routh-Hurwitz criteria in the next video. Thank you for watching.